more you train, the more you see circuits like this, your eyes can figure it out by itself. You automatically gonna see if it's a delta or Y combination. But this time I redraw that. So this is 1.5 ohm. I have still 1.5 ohm. This is fine. I do not care about the 400 ohms. It's just 400 ohms and stuff. Okay, so the left part we don't care right now. Mostly it's these resistors that's we want to simplify it, and we want to simplify it as much as we can. Oh, sorry, what happened? Okay, so you can see that's 50 ohm resistor. I can put it like this. I haven't. There's no change in the circuit's properties. It looks only different in your eyes, but for the circuit, it's just the same as this one. So I have 50 ohm resistors. I have 50 ohm, 100 ohm, and 100 ohms. But instead of having it as a kind of rectangle, I can make it to look like a triangle, just for the appearance for you guys. So can you now see something? Yes, because you can see that this looks like a delta. Oh, if it's a delta, I can superimpose a Y inside a circuit. Sorry about my bad drawing. So at first I drew it in OrCAD, and then I did it with the paint. So sorry about this, but you know what I mean. So 50 ohm resistor, 100 ohm resistor, and the 50 here. So I have. I hope you can see my mouse, else you cannot follow. Okay, so now this is the Y, which is superimposed inside the delta. What does it mean? It means now I can use the relationships that I can go from delta to Y. Since I know this delta, in this case, say 50, 50, and the corresponding resistor for this one would be 12.5 ohm. This resistor would be 25 ohm, and this resistor would be 25 ohms. So now I can go from a delta combination to a Y. Exactly same thing I can do for the lower part. The result will be 24. You can compare this one. I will upload the PowerPoint on this learning when I'm done with this one. So you can go, and you can also go back to the previous slide, and you can see you can compare it with the relationship. Okay.
Elias?
Yes, please.
Can you go back to the formulas?
Yes. The formulas. Yes. Here. So we have
the other ones.
Yes.
Yeah, there we go. There's a typo.
You probably B. RB is this one multiplied by RC.
Yeah, but your denominator is RA times RB times RC euro, but it should be plus instead.
Okay, that's a good catch. Probably. Let's see. Yes, there's a plus. So there's a typo. Yeah. Good catch. Very nice. Yeah, but I think it's a typo. Yes, but the result is fine. 12.5. It should be. Thank you very much. That was nice of you. Okay, so from this now we can see that we have transformed from delta to Y, and then let's redraw. So we redraw this circuit because the red is originally what we found was this black resistors, let's say. So that means it will look like this. I took it from the picture from the book we have. Since when you rotate resistors on a very sharp angles on OrCAD, it doesn't look fine. So that's why I took a picture, a screenshot from the book instead. Yeah, and also that I'm really bad on drawing resistors on paint. So, but you can see that if I transform from delta to y, my circuit looks like this, kind of relieving. So what does it mean? It looks kind of like this. See, let's look at this. I have 1.5. I can now add it to this 12.5. That gives me 14. I have 18 ohms here. Then you can see that 25 is in series with 71, which is in series with 24. Haha, that gives me 120. 25, 31, and 224, sorry, they are in series. I can add them. It gives me 80. Look at the circuit. Got so much simplified. So happy. Now I have what? I have now two parallel configuration. But there was a question before. Yeah, it was now we have a parallel configuration. So what I can do, I know how to do that. I know how to put these two as a parallel and then as a series. And then I have only one resistor. Isn't it great? Isn't it great that we can simplify a circuit that looks so crazy that we have almost no idea, no chance to simplify it. But this goes to a bit of transformation. So you need to sharpen your eyes, how to see a delta. I can see a delta here. Oh, and go from delta to y, or sometimes you go from y to delta transformation. Depends on the circuit. So we use a relationship. Here's a typo. Remember that. And then we redraw the further simplification, and then we can use our old trick, the parallel and the series configuration stuff, and then we can make it to only one resistor. Isn't it great? Say yes.
Wasn't the exercise to find the power dissipating 31 ohm resistor?
Yes, you can do that. That was the exercise. But I took it further, that you can see that I can make it to only one equivalent resistor. Here, find the resistance seen by the ideal voltage source in the circuit. What does it mean? It means that if you are this source and you want to see what is this resistor, for the source, it doesn't matter if it's complicated as this or if it's only one resistor. It doesn't matter. For the source, it looks only one. It looks as just if there was just one resistor. So either one resistor or a complicated circuit as this. So in order to find the resistance seen by the ideal voltage source in the circuit, then we need to do all those crazy simplification. And then we found what? We found one resistor. And what is that? What is the value? I calculated here. Since we haven't calculated since 80 and 120 is in parallel. So 80 and 120 is in parallel. We know how to add two parallel resistors. And 14 and 18, they're in series. So we need to simply add them. It will be 80. So what does it mean? This equivalent resistor seen by this voltage source is 80 ohms. So what we have learned how to simplify a circuit, which is neither a series nor parallel. We use the delta to y or y to delta transformation to make our life easy. And but if you want to do it in practice, you simply disconnect the power supply. You use your ohm meter to see, okay, what is the resistance? And that's you go. But you say, hey, you spent so long time just explaining how to find a resistor. You take your volt multimeter, put it to ohm, measure the ohm. Yes, that's true. But sometime again, most of the components, they are in a boxed shield. You have no access to it and you cannot do it. You only have maybe access to the diagram, so you cannot measure it. So this was part of the exercise. Again, the thing is, once you know the characteristics, of a circuit, and the current and the rest will fall by itself. So it will be easy. Good. I will not go to find the current and stuff. It's yeah. But the main idea was that how to simplify for this part. Good. I will upload this one on your it's learning. Yeah. So you still see my my PowerPoint. Are you guys there, or am I talking to myself?
Yeah.
That's good. Oh, 29 people. It's a record, I think, so far. It's called a triangle. Pap. What do you mean, Pap? It says it's called a triangle. It looks like a triangle, of course, but it looks also like a delta. You know the Greek symbol delta? Yeah, that's why it's called delta. But you can call it triangle. Okay, guys, are you good to continue? Can I go to move to the next topic? Are you guys okay?
Elias, can I show you the input problem?
Yes, please. Okay, guys, we let's say we take a very short break for those of you maybe need a small break. But I will continue right away after looking at Marius's problem. Okay, let's see. It's a lie. Okay. Right board.
Okay, this is only when in the code print command is used, but if I enable input.
I think I know. Do you have any one of those mentioned IDEs installed?
I missed half of the lecture.
Yes, he have it. He have Python craft.
Try to get MicroPython craft and try to I think you not have a problem if you do that, because if you use input, somebody's saying.
Yeah, but in the book it says use the command prompt. That's why we using it. That's why we installed the MP or what it's called.
In MicroPycraft, there's also like a sort of command prompt that you can use where you don't have to do all kinds of weird things. So
yeah, but we were just following the guide in the book.
Yeah, it's good. It's good to follow the book. Of course, it is good. But since I cannot see everything here, it's yeah. But what I did was that I didn't follow the book. I used the IDE, I used the eExplorer, and I used MicroPycraft. It worked fine. So I would recommend that you please use those IDEs. Not because the REPL is useless. It's good to know that one. But when it comes to uploading and programs like this, the good thing is that your code will be saved. One, you can go back and edit it. Since when you're in the REPL, then everything will be lost when you disconnect and you take the power out. Then you again, then you have to do the crazy stuff by activating the your virtual environment, find the port and stuff. if you're using the IDE, it's a bit easier to get to. Yeah, so I would recommend Marius, please use the IDE instead, and for the others as well.
Which IDE again?
It's called the UPyCraft.
Okay, thanks.
I maybe can show you. I write, I think, on the chat. I think it's called UPyCraft, like this. Okay. Okay. Please, Marius. That's good. Let's have a look at that one again when you have installed the PyCraft. So I need to continue with two other topics since we have a lot of stuff to cover, or I have to cover a lot of stuff, and you guys should be able to follow and stuff. We have a meeting in the middle of the lecture. Okay, I need to find. Give me 1 second. Pap is saying, what's happening at 12:30? Somebody said please invite us to somebody, or I might be dumb. No, it's simply the other lecturers, Per, Nikolai, and Ruslan would be here. We're gonna have a discussion about. I think it's about how the courses so far from like last semester and this semester. It's mostly your feedback regarding these courses. That's it. So I do not know if they join my Google Meet room. Probably Pia has sent another link. I will check on that one. Pub. I do not know. I don't think they will join our class. We will find out. So you guys can see my PowerPoint. It says superposition and maximum power transfer.
Yes.
Yes, we can see.
That's great. So what does this superposition mean, and what does max power transfer mean? Just a bit of overview. I hope you remember the differentiation from your math. If not, so I would say please refresh on that one. So we will talk about the max power transfer and the superposition. Just for those of you the math and the differentiation is a bit rusty, let me tell you what this is about regarding the differentiation. So think you have a sheet of paper in this, and you want to make a box, and you want to optimize it. It means that you want to make it as big as possible. So how are you going to do that with this this much of sheet listing or cardboard you have in available? But the solution is that normally when you have normally we have an equation. So an equation can be like this. When you differentiate an equation, I wish I had time for this one to go through and teach you how to do differentiation, but again, due to the time, I cannot do that. Sorry. So maybe you can see a YouTube video on differentiation. It's not that hard. So the only thing I need for this part of the lecture is that how to optimize power transfer, and that's why we need this tool from math, which is called the differentiation. Okay, say that I have now the volume of this box that I made, which is called 140h, which is the height, minus 48h squared plus 4h to the third. So v dash h, it means that my function is as h, and v is the volume, and this dash it simply means that I will differentiate it. So whenever you differentiate, the power goes down. The power, when I say power in math, it means completely different thing when it says power in electronics. Power in math means that, for example, this 2, h to the power of 2, h to the power of 3. So the power goes down. So that means that you subtract 1 from it. So the only I have is 140. So 2 minus 1 will be 1, h to the power of 1, plus 12 h squared. So, sorry. So now I have differentiated. What does it mean? If I put that one, v equals to 0, there's always, if we want to optimize a function, optimize whatever, you let the solution to be equal to 0, the differential part, and then you solve it. So that means if the height is 6.08, then I would give the maximum volume, which would be 120. Again, this has nothing to do with our lecture today, but this was just a kind of a fresh, a very short refreshing of differentiation. But again, if you have any question regarding that one, so please, we may take it on some other time, or try to see a video on differentiation. Okay. So a couple of weeks before, we have seen a network, a linear network, that could be replaced by only a source and a resistor. And it may look like this, that I have a voltage source and a resistor. And we call this one R Thevenin and V Thevenin. So that was the lecture, I think 3 lectures ago, that we have talked about this one. Sorry, guys. Or the other one was that my linear network can be replaced by a source and resistor. Can be Norton current, N for Norton and I for the current, and resistor. So this was the 2 ways we can represent a linear network. A linear network is, again, imagine you have a complicated circuitry, shield in a box, and only thing that you have access is the 2 ports, just the 2 leads or the 2 wires coming out of that. But we have learned on previous lectures how to model this one. Well, the way we could model that one is that it's only a source and resistor, and it can be used. We can use either the Norton or the Thevenin, or we can go from one to, if we have information about the Norton current and Norton resistor, we can also go to the Thevenin voltage and Thevenin resistor. So please see the previous lectures, PowerPoints, if those of you missed the course, the lecture. So the question is that what load, RL, will draw maximum power from one port network? But let me clear this one. Why this this is important. Why we talk about maximum power? Okay, imagine this one. Let's say you have two systems that you want to connect, and you want to have the best. Imagine this one. If we take it as sound, let's say that you want to connect two boxes or two circuitry that they talk to each other, and we want to have the volume of the sound to be transferred from one system to other system at its maximum, so nothing is lost. So we get the best quality sound. Let's say that's what comes for example, the maximum power transfer. That's why it's needed. You need to know, like those companies that they make the perfect what's called earplugs and microphone and stuff. They definitely use this method, that they go inside and they look at their circuitry and they fine tune it to the point that they have the maximum efficiency. And so when you hook your, let's say your plug to want to listen to music, and you get the maximum out of that one. That's why some companies they make best appliances like sound. Some of them do not. It all depends how, if you fine tune they do on the circuitry to deliver the maximum power. When I say power, that can be anything. That can be current, voltage. That can be it can be also the sound. So this is the idea behind it. I mentioned the sound as an example, but it can be anything. So nothing is lost during the transportation. Let's say you have a wire and you have two systems connected on the end of those wires. And these two systems, they can talk, communicate without any loss. And how to do that? Okay, so you have this linear network and you have a load resistor. So how can I get the most out of this? How can I get the maximum power delivered to the load? That's the best thing. So what I can do that, of course, I can replace my linear network to be as a Thevenin voltage source and a Thevenin resistor, and I can now put the load resistor. So this is a continuation of what we did last a couple of lectures before. So if the linear network can be replaced as a source and resistor, as you can see it right here. And now I've attached my load resistor. Again, load resistor can be anything. So let's do the analysis. So the reason we learned the analysis during the last semester and this semester is because we need it. And you can also see this, how I build this course is that it all is like Legos. That one lecture is dependent on the lecture before. So in the beginning of the course, I was so much insisting that please do not miss the lectures. Or if you, for any reason, do miss a lecture, so please look and read the previews before you go to and continue a lecture. Because the things that I talk about today is most of them are actually is mostly dependent on the things that we learned on the previous lectures, and the tools that we learned they are on the previous lecture. So for those of you who have where it looks a bit weird right now and you fall apart, it's okay. Don't be discouraged that you missed maybe a lecture or two. So if you consult the previous slides and PowerPoints I've put on the previous weeks, then you will be good to continue. But please continue as much as you can right now, and you can ask me a question later. So no problem with that one. Good. So now we can use our circuit analysis. Let's say if I want to know what is the load current for this, well, we know how to write that one. So that's simply the V Thevenin divided by, well, this is a series circuit. We know in series circuit you simply add two resistors. So, but resistor we talk about this, and this is I call it R Thevenin and RL. So the current is simply my source divided by two resistors. Okay, not big deal. What about the power delivered to the load? Well, we know what power is. But there are different ways to write power. One way is that you can say, hey, power is simply, just sometime I need to ask, can you still see the screen? The sound is okay? You can see my mouse?
Everything is fine.
Great. Nice to hear that. So power is now equal to I squared, current squared, multiplied by R. Well, if I know the current, well, how to know the current? Well, I can know it by simple relationship we learned in the first semester. Source divided by resistor. Well, in this case, I have 2 resistors. So I simplify it. I have 1. You can also say this is my total resistance. Anyways, then I know what the power is. Okay. So the power can also be written at I squared, since this is I squared. Then instead of I write this equation, which is the V Thevenin divided by RTh, which is the Thevenin resistor, plus RL. Yeah. So this is the relationship. By the way, the thing is that what we have to do is that to find the maximum power. The reason that I've shown you the first math example was that we use something called in math. For those of you who do not know differentiation right now, it's totally okay. We use differentiation. It's a technique simply that you apply to an equation in order to get and find the maximum output. For example, in the previous example, let's say you have a piece of paper and you want to make a box. And the question is that, hey, how can you make a box which is the maximum volume? Because you can make different size of the box, which have different height and width and yeah. But how can you make a box which is which can output maximum volume? So first, what we did was that we know how to find the volume, the height times the width times the what's breadth in English, width, length, yeah. So length, height, and the width, you multiply them, you get the volume. So then you take your equation, you differentiate it, so this is the first step, and you let it be equal to 0. And once you do that, you find a solution. And then the result will show you what will be the maximum volume. The same technique we will use. That's why we need differentiation. For those of you who had mathematics in B niveau, they do not have math differentiation as a part of their curriculum. So sorry about that one, but this is required here in this lecture. But anyways, you can catch up on differentiation later. So what I have right now, I have my equation here. Where's my mouse? Here. My mouse is disappearing. Okay, somehow I cannot here. So I have an equation. I want to differentiate it with respect to the load, with respect to resistance. So again, please do not, and I insist, do not discourage what I'm showing in a couple of clicks. But I will show you, for those of you who do not know, do not remember differentiation, a trick how to do it in MATLAB. So again, please do not discourage what I'm showing. Yeah. So this D stands for differentiation. So I want to differentiate my power, which is delivered to the load with respect to the resistance. This means that I differentiate the power with respect to the load, and I let it equal to 0. Once I do that, instead of on the right hand side, I write my equation and I will do the differentiation. Again, I will not do the manual differentiation. I quickly go and jump to how to use the MATLAB. Since this is the focus is not math, the focus is how to apply it. So for those of you still saying, holy, holy math, don't discourage. So this is what we do. you can see here, I write my equation, which is, hey, power is equal to V Thevenin squared multiplied by RL divided by RTH plus RL squared. So this equation came from what? It came from applying a small analysis. We found the current, and we want to know what the power was to this load. Nothing else. You can see, I'm so sure that all of you are able to get this equation from this source and two resistors. Again, for those of you who have missed, what we want to do is that, or our mission is to transfer maximum power to the load. So there's no loss when we connect our load. Okay. So the equation was this one: V Thevenin squared times RL divided by R Thevenin plus RL squared. There are two ways we can do it manually, hardcore math. I will not do it this time since I cannot see you physically, so I can write it on the board and stuff, and it takes a bit of time. And I know most of you do not like math. That's something I have noticed. But I can show you another way how to do that. So for those of you who like math and hardcore stuff like this, you can do it like this and simply differentiate manually by hand. Yeah. Else, we're gonna use our friend MATLAB. Simply write your equation. All you have to do is write DIFF. DIFF stands for differentiation. Okay. So I would encourage you that you test your this piece of code on your MATLAB, and please do that so you get the same answer. Okay, so I write my equation. I want to differentiate P, which is power, and I write a comma, what with respect to RL. I want to know the maximum power transfer from the load to from the source to the load. I made a mistake, I think, here because undefined function, because first I wrote a small p, and I say, hey, do you mean power? Yeah, of course, because I defined my power with big letter P. So, and in the beginning you need to write sims. You need to define the variables, the V Thevenin, RL, and RTH, since we are using them. So this two line will lead you. So the answer would be that you get something like this. This will be your differentiation form of the equation, and then we set it to equal to 0. So whenever we set it to equal to 0, sorry, we're gonna have an equation here. And this is exactly the same thing that MATLAB also gave us. What the takeaway is actually this. So for those of you who have missed or confused, just remember this one, that in order to know what is the maximum power transfer from source to the load, all you need to do is what? Look at the voltage, the Thevenin voltage, square it, divide by R Thevenin multiplied by 4, and that's it. So please do remember this one. Forget, I will not say forget what I've just explained. Those was simply to get you to this point. So again, the takeaway is formula in this red rectangle. In order to know the maximum power, all you need to know is the voltage and the resistor. Voltage should be squared, and the resistor should be multiplied by 4. And that's what we do. So if we have, let's say, a source and a resistor and a load, let's say we have our load is sorry, this our source resistance is 25. And we know what power is. Power is simply I times I squared times Ri. Normally I show this one on the, normally I test this one with the power supply and a resistor. I cannot show that one, and sorry about that one. So as you can see, if I take, but instead I show you on this Excel sheet. What I do is I sweep resistance from 0 to 100, let's say. I sweep my resistance from 0 to 100. And then I want to know what's the power. Well, power is simply I squared times Ri. So if I know the current and if I know the resistance, then to find power is simply I squared times R times I. So for this example, let's say, what I do is that I sweep the resistance from 0 to 100. Again, this is a theoretical example right now, but we can do it in physically, of course. Then you can see that I can plot. If I plot resistance divide as a function of power, I get something like this. And you can see, haha, at some point, at some resistance, you get the maximum power. What does it mean? It means if your resistance, if your load resistance, if you choose your load resistance, let's say at a point where you have the maximum peak, then that's the maximum power. That's the fine tune, and that's the beauty of it. And that's the when you make a nice product, and that there's no loss. And there's by loss mean that, so for example, let's say you're making some sound quality sound transfer between two ports, for example, between two circuits, then you know that nothing is lost. You get the best quality out of it. And this is how do you do it. And what was the takeaway? So this is what you have to remember, that the maximum power transfer is the Thevenin voltage squared divided by R Thevenin times 4. And the reason I showed you the circuit analysis, and I showed you the differentiation and the crazy math and the MATLAB is just how to get from this. This was our mission. Had a circuit and how to deliver the load to so at this time we had no idea. We had no idea of how the formula look like. I can of course give you the formula. Hey, this is the formula, and go and apply it. And you say, so where this formula came from? Well, this came from the knowledge that we have learned circuit analysis, and the things that we have learned so far. And we use a bit of math here. We differentiated, and then we came to the point that the maximum power is simply this one. Good. So again, the takeaway is this formula for maximum power transfer. So let's take an example. At what load value we have on this R0, does maximum power transfer happen for the following circuit? So we have a circuit like this. Looks so crazy, I know. And you say, how can we do that? We have no chance. But I would say, no, you can do it. We have all the tools learned by this point. So we have okay, sound check. Can you hear me?
Yes, everything is fine.
Smoked. So I have source, a power source. It's a independent voltage source. I have a dependent current source. This means that the current depends on the value somewhere else in the circuit. Again, where have you seen something like this? Well, a transistor maybe, because depending on how much you lit the base current, the collector to emitter changes. So something like that. Okay, anyways, we do not care about the details, but let's say we have a circuit like this, and we want to know what would be the maximum power transfer. Good. And we can also find the maximum load power. So let's say this is my RO that we want to attach. First thing first, let's find the short circuit current. Again, the theory behind this one was covered, I think 1 month ago. So short current, what does it mean? The moment you put a short, what happens is that the resistor which is in parallel, that gets in trouble. Why? You know, by this time, because the moment you put a short, current wants to go to through the least path of resistance. Well, this piece of wire has almost no resistance. So why not going through this one that compared to going through the 40 kilo ohm resistor? So for the current comes from somewhere here, and there's 2 nodes, it doesn't want to go through this one. It's hard, it's traffic, it's misery. So that's instead the current goes through this piece of wire that they've shorted. So for the current, this is as if there is no resistor. Yeah. So we can say, fine. Let's find the mesh current. Mesh current, what does it mean? Oh, by the way, if I remove this resistor, the circuit looks exactly like this. So there's no magic right now. I haven't done anything. I simply put the short circuit current, and the theory behind this we covered again 1 month ago. So I'm not going through that one. Okay, so let's find the mesh current. There we have a loop there. We will call it I1. I have another loop there, and I have another loop here. And I can say whatever current that circulates in the third loop, which is I3, that's exactly the same thing as current, as the short circuit current. For those of you who forgot about short circuit current, it's just the current that it's going through the wire when you put a short. So you can see that this relationship is because that whatever current goes here is exactly the same as I3. The reason I write it is that it can simplify our work in later analysis. Good. Oh, our old friend Kirchhoff. So let's apply his law, his voltage law, on the first one. This is boring stuff, I know, for most of you, but let's do the dance one more time. So our convention was that when it's a voltage source, we always put a minus because it delivers power, and we take what? Voltage is simply I, which is the current, multiplied by resistance. Resistance is 2K. 2K, of course, yeah, you can write it as a 2000, and you multiply by the current I. Okay, and then you add the next one, the 20K or 20,000 K, 20,000 ohm. Just for a quick refresh, you see, hey, why are you multiplying by I1 and minus I2? Well, the reason is that if there was no, I wish I had my hand so I can cover the rest of the circuit, but I cannot do that. So if I do not have the I2, then it will be simply 20,000 multiplied by I1. Since there's also current going, if you can see my mouse, so I2 is going in this direction. It's going against I1, and I1 is going clockwise. I2 is going, I2 is going counterclockwise at this meeting point. That's why I need to take I2 out of it. That's why I subtract that one. And I let everything equal to 0. Why? It was what Kirchhoff taught us. The Kirchhoff's voltage law. Okay. Sorry. KVL around mesh 2. Again, we have to do the same dance, but I am not doing it. You have to do the dance yourself now. And the same thing we can do for I3, and the same thing we can do for the rest one. So I can now give you the overview of all this. We have now 3 equations with 3 unknowns. What we can do is that now I can find I can solve it. I can solve to find what the current is, using the techniques that we have learned so far. Okay. On 1 month ago, I remember that we had a lecture on how to find what's called the total resistance of a circuit using the alternative method. See, you may see I have the exactly same circuit. What I do is that that I've removed the voltage source. So I remove the voltage source in order to find the equivalent resistor. So if I do that, I put a voltage test of, let's say, 1 volt, just to see how much, what would be the current. So there's an independent node there, and the current direction, it doesn't matter how we put the current direction. Let's say I do not know at this point the VX. Where's my mouse again? VX. Let's say the voltage at this node, I do not know that, but I can find. And the way I can find is that I can apply the KCL, the Kirchhoff's current law. You can see I'm using over and over this KCL and KVL, and you maybe by this time get so much, maybe amazed that how it's possible to simplify a complicated circuit by very simple rules and methods like Ohm's law, Kirchhoff's law, and that's it. You can see I'm still using those old tools to simplify my circuit. Again, this we have by now. You all know how to write a KCL at different nodes. So now I make a KCL for Y. The reason I'm going fast at these slides that this is what we covered last semester. So this will be the equation for the KCL at node Y. So all in all, now I can solve these 2 equations using MATLAB, our friend. The result is given 0.08 and 0.3. And the last thing, we need to apply at node A. We also need to apply KCL. The current will be Vx divided by 20K. And if I substitute the values that I know so far, then the equivalent resistor will be 20 ohms. So what does it mean? Equivalent resistor means that I can simplify this circuit. All these resistors can be replaced by a 20 ohm resistor. Well, in reality, if you have a circuit like this, you simply take the voltage source out and you put your multimeter and you simply measure the what's called the resistance. But in most cases, you do not have access to do that. So that's why you need to do this analysis by yourself. So 20 ohm. So the Thevenin voltage will be 14 milliampere. This is what we have found. Multiplied by 20K, so 280 volts. So R0 or the load resistance must be 20K. So what we have learned in the previous PowerPoint, that in order to find the maximum power transfer, all you need to know is that the Thevenin voltage and the Thevenin resistor. So now I know the resistor is 20K, which I found it by simplification of the circuit. For some of you, I'm so sure that you kind of, maybe you lost me because maybe it was a long time ago we had those lectures. Yeah. But the alternative would be that when you have, let's say, ORCAD as a tool, then you don't have to do this analysis. So you simply use the example that I showed you. You simply ask for what will be the total resistance. And if in reality, in practice, if you have a circuit like that, you simply measure it. You measure the what would be the resistance, and if you know the voltage, the definite voltage, then you know the maximum power transfer. So in this case, we did everything manually. We did everything on paper. So the Thevenin voltage was 280 volts. This was given. What we found was the Thevenin resistance. So all those effort was simply just to find this resistor. So now I know the maximum power transfer from the source to the load is 0.98 watts of power. So,
Elias, are you still alive?
Elias, my boy, you there? Somebody take over the lecture.
If the teacher doesn't come back in 15 seconds, we're legally allowed to leave. Rune, talk for a second. I want to hear your shitty ass voice.
Please don't.
3 o'clock.
Oh, okay, fuck.
When Mario speaks, it sounds like a rusty bike on a Russian road.
Good one.
Sorry, couldn't respond with screaming laughing.
This is the best part of the lecture so far.
True.
Jonas, are you there?
I'm not gonna lie, I also like the fucking 40-minute introduction to the ORCAD courses.
I think Jonas should take over.
Jonas, you've been voted.
I agree. It's just because I'm old. Shut the fuck up.
Old and sexy, you forgot.
Yeah, beauty before age. Of course he's not. Why use internet?
I couldn't hear you, sorry.
Hello, guys.
Hello.
What just happened? You just disappeared.
I know it disappeared. The funny thing is that I was talking about maximum power transfer, and then I got the power outage on PC. So, but anyways, I'm back. The PC is reboot, and okay. So where were we? Can you hear my? Is the sound okay?
The sound is fine, but you have some background noise.
Background noise. Let me fix that one just in a second.
Sounds like a dragon is waking up.
Sounds like a cow having, the runs.
Just a second. I'll fix that one. I put my headphones on.
On the cow?
Sorry?
Nothing.
Yeah, it was. Is the sound okay now, or is it still?
Sounds fine.
Yeah, there's no alien sounds.
It's okay. So sorry about the power outrage. You may hear some sound in the background. It's just the workers. They start building stuff. So it's not much left from this from my side. So let me accelerate a bit. Okay. Let me show the window here. There we go. Okay. Can you see now my PowerPoint?
Yes.
Sorry, what?
Can you see the screen?
Yes.
That's great. So what we did was that we successfully found the amount of power